Okay, so whenever we say that f is a function from I to r, so we actually mean I to be an interval, okay, of r. So what is this actually? What do we mean by this? So let us try to understand the term f is a function from I to r, and why do we say so? So this understanding is important. People are still joining in. Just a minute. Okay. Now you see, let me draw a function. Say for example, let us draw an axis. This is your y-axis, and this is your x-axis. Okay, and let us try to draw the function of fx equal to mod x. Okay, so we can write and draw like this and like this. Okay, and this point, I can consider this point to be -1, and this point to be +1, and that is 0. Okay, so that is my function fx equal to mod x. Now let me do one thing. Let us just wait. I'm saying what I'm doing right now. Okay, and let us draw another set like that. We are always familiar with these diagrams, and we are familiar with these definitions maybe, but we are not familiar with the way to picturize the definition for better understanding. So I'm trying to tell you how to visualize things. So if you visualize in my way, if you do this particular practice, then you will be benefited. Now what I have drawn over here, I have taken the pain of drawing several vertical and horizontal lines. You can consider each of these vertical lines are actually the replicas of the original x-axis and y-axis. Okay, so actually all of these horizontal and vertical lines are actually what? Real lines. So whenever I am saying, suppose I am taking this interval I'm considering that is your I. This interval is I, obviously this I is actually the subset of this entire real line, from stretching from -infinity to +infinity. Okay, both ways, in from horizontally as well as vertically. Now I is just a subset of that, but because we know r is -infinity and +infinity, r is also written in this manner. So definitely I is a subset of r. And whenever I'm defining a function, say f is defined from I to r, here f is the function which I have defined is from -1, 1, this interval to r. I have defined this function by fx equal to mod x. What do we mean by that? Whenever you are selecting a point, in this interval, you are getting a point over here. Whenever selecting an interval, you are getting a point over there. Whenever you are selecting a point over here, then you are getting a point over there. When you are selecting -1, you are getting a point over there. Okay, so you see that each of these points which I have drawn, and many such points can be drawn, each of these points are actually falling on the replicas of the real lines, whether vertical or whether horizontal. This point is falling on the replica of the vertical real line, and this point is falling on the replica of the horizontal real line. And therefore they said that, okay, whenever we choose a point from this domain, the image is on the real line. Okay, don't think that don't draw this real line, and don't think that the image is falling on this real line, on the replica of that. And therefore in the two-dimensional plane we get this kind of figures, okay. So therefore, probably by this definition we have understood what I mean to say. Whenever the image is getting mod x is falling, the values mod x will are falling on the real line, not on the original real line, but replicas of that, maybe horizontal or maybe vertical. So that is what is meant by f from I to r always, okay. Now they are saying that the function icon is said to have a relative maximum at the point c, at the point c belonging to I, at the point C belonging to I. Now, probably suppose if I try to look at this from the viewpoint of mod x. So suppose this is my point C. This is my point C. Suppose, okay, and no, sorry, not C. Sorry. This is the point C, and suppose uh, according to this point, this part is my f of c. This part is my f of c. Now, what is it saying? That if there exists a neighborhood v delta c, so you are choosing your delta, choose your delta, select a point, which is c. I have chosen it in the interval, sub interval -1 and 0, okay. And with respect to c, we are getting fc, which is equal to mod of c, obviously, which is positive, so mod c over here. So this is the point, and they are saying that now you choose your delta. Say I am choosing my delta is 0.01. So suppose this is my interval. So suppose this is my interval. Then they are saying that if f of c, this point f of c is, if f of c is greater than or equal to fx for all x, in v intersection I shall talk about v intersection I later, v intersection I, then this we can say that this particular point c, if this happens, we'll say that c is the point of, c is the point of relative maximum. C is the point of relative maximum. But in this particular case, it is not happening. In this particular point, this is not happening, because however small you make your interval c minus delta and c plus delta, then you will see that there are some points which will be uh, greater than fc, and therefore you cannot say that c is the point of relative maximum over here. It is not here. In this particular case, it is not happening. C, at least c is not the point of relative maximum, okay. Now suppose and similar is the case with relative minimum also. C is also not a point of relative minimum. So here we can say that according to my diagram, neither C is the point of, this is the definition actually. So here in this particular case, neither C is the point of relative maximum, nor C is the point of relative minimum. Okay, so it's not happening. Now suppose I want to understand this part, V intersection I. So what do we mean by that? Why V intersection I? Why not just V or just I? Okay, probably you are thinking that. Suppose this is my boundary. Okay, so suppose I'm choosing a point very near to 1. Say this point I'm choosing. Suppose this is my C dash. Okay, now according to this point, this is my this is my FC dash. This is my FC dash. Okay, and I am choosing C dash, which is less than 1 but very near to 1, very near to 1. Now you see that whenever it's too close to 1, as close as you can make it, but it is not 1. Now you want to study whether this point C prime is the point of relative maximum or minimum or not. Then you are choosing your delta, and suppose you are getting a interval like this. So you see that this point, I want to say whether this C is relative maximum or relative minimum or not. For this, what I need to for this I need to select points, and these points will lie, because this interval you are considering, this interval is your V, and the total interval is I. So you can select a point which is, suppose this is your point 1. Okay, so some parts of the interval, I hope you can see it, this portion of the interval is falling outside the interval. C minus delta and C plus delta. If I choose this C minus delta and C plus delta, these 2 points, with respect to these 2 points, some parts of the interval, C minus delta and C plus delta, I'm writing it C minus delta, and that is C plus delta. Right hand side part is falling outside the interval, but we are only concerned about the interval itself. We are only concerned about the interval itself, and therefore we need to consider points x. We need to consider points x, which will be the intersection of C minus delta and C plus delta with the original interval I, which has been considered. Okay, and therefore V intersection I has been written. And since this is a case which can happen, so in general they have written V intersection I, but for points like C lying in intermediate between the interval, V intersection I is simply equal to, V intersection I will be simply equal to V. So I'm writing over here, for any intermediate point C, as has been drawn, V intersection I will be simply equal to V. But if C lies very near to boundary, if C lies very near to boundary points, then V intersection I is not equal to V. So to generalize the situation, they have, in the definition they have introduced the term V intersection I. Okay, so that is the thing, but it is not happening for these points like C and C prime. Okay, so that is one sort of analysis. Okay, another analysis that I want to make is, say, for if you consider a graph, I'm now considering an arbitrary graph like this. So for example, I'm considering a graph like a graph like this, and suppose this graph is actually what it's, I'm considering a part of it. Say for example, I'm considering a part from here to here. Okay, that is my point of study from here to here. So this, suppose this point is say for example a1, and this point is a2, and suppose this point is your fa1 and this point is your fa2. Okay, so if this is my interval, so this is my interval, and I want to study whether this interval has some relative maximum or relative minimum at certain point or not. So if I want to study, and diagrammatically you see that if I select a point C over here, and if I draw f of C like this, okay, then you can choose an interval C minus delta and C plus delta, C minus delta and C plus delta, within which, if C is contained in this interval, you can say that, okay, let us draw it. This is the vertical line, this is another vertical line, this vertical line is your f of C minus delta, that vertical line is your f of C plus delta. So inside this interval, if you choose any point, choose any point x in C minus delta, in C minus delta, C plus delta, with intersection a1 comma a2, if you select a point like this, okay, then you see from diagram, it is clear that all the points fx, all the points fx is greater than or equal to fc. All the points fx are greater than or equal to x, and it is true for all x. And similarly, if you select a point like say for example here, I am selecting a point, and suppose I'm considering my interval, I'm considering my interval from a1 to say a5. This is my interval of study now, and in this interval I'm getting a point say let us denote this by c1, and we are getting a point which is called f of c1. Okay, and therefore if I select a delta, I mean, let us select delta prime now. In this case, select delta prime, and the interval becomes c1 minus delta prime and c1 plus delta prime. Okay, then within this interval, you see if any x falls within this interval, if you select any x, you can choose x as close as c1. You will find that for this case, fx is less than or equal to fc for all x in the interval c1 minus delta prime, c1 plus delta prime, intersection a1 a5. Okay, so you see that this then we can say that then at this if this happens, this was not happening for my previous curve, but this is now happening for my this curve, a portion of the curve. Then we can say that in this scenario, C, this point C is a point of relative minimum, and here I can say that, okay, I consider this as C1, so let us write it as C1. We can say that C1 is the point of relative maximum. Now I do not have any notes. Okay, my part, I didn't prepare any notes for teaching you. I'm just whatever coming to my mind I'm saying, but I hope some of you are actually copying what I'm saying right now, because these things you are not going to get in any book. These things are entirely mine. So if a particular student can write it in a better way, if his student can, I am telling all the students, if any student is there who is copying everything properly as I'm showing, then I may ask him or her to give me his or her notes so that I can again go through that what I have taught. Okay, so just for my record, but I don't have any notes, so that's why I'm saying. So it is up to you. If you are not copying it, then it is all right. I'm not telling you to copy. If you can understand, then you may not copy. But if you are copying, then later I may ask note for this. Actually do not prepare mathematics note ever. Now, so this is my point C1 and point C and C1 as point of relative maximum, relative minimum. Okay. Now, the question is why to study mean value theorem? Why do we need mean value theorem? That is a very important point. Okay, so probably if you have gone through the note, you will find that there is a line written in the book, in the chapter, in the section 6.2. And if it would be nice if I read the chapter line from the book itself. The line is saying that the mean value theorem, which relates the values of a function to values of its derivative, is one of the most useful results in real analysis. So actually, mean value theorem, this connects the values of a function to the values of its derivatives. Okay, so they have written this derivatives. Now immediately a student can ask me, and that has not been said in the book, why do you want to connect the values of the function with the values of the derivative? If you observe carefully, and if you can recall, in the school you have studied that derivatives are actually giving you an idea about tangents. Okay, idea about tangents. Now, so whenever we want to connect derivative of value of the function to its derivative, actually we are trying to, this means that we are trying to connect. Actually, this means that we are trying to get to know the uh, get to know about the tangents about the tangents uh, at certain points. Okay, and if the student asks me that why do you want to know the tangents, why you want to know this the not, I mean, information about the tangent at certain points, then you carefully observe the figure. Okay, the answer lies in the figure. The figure is actually saying, if you find that in this case the point C was the point of relative minimum. Now here you immediately can see that this, if I draw a tangent, this tangent is actually parallel to the axis, horizontal axis, x-axis. And here you can draw a tangent which is parallel to x-axis. So in the point of relative minimum, in the not in the sorry, my article is at the point of relative minimum, at the point of relative minimum, and at the point of relative maximum, in both the cases, relative minimum, the point is your C, and relative maximum, my point is C1. In both the cases, what happened? In both the cases, you will immediately say that f dash c is equal to 0 and f dash c1 is equal to 0. Okay, so because the tangents are parallel to x-axis, so the ultimate objective of a mean value theorem is, why do we want to connect, these values of the function to the values of the derivatives? So is that if you consider the functions like fx equal to mod x, fx equal to x square, fx equal to sin x, fx equal to cos x, all these graphs are known to us. But suddenly, if I ask you that, say this is your function, uh, uh, 2 sine 2x into sine 1 by x plus cos x, this is your function. Immediately you will take some trouble, you will take some pain, but immediately you cannot say that, and if I give you the interval like minus pi to plus pi, this is my domain, because without domain there is no point in studying function. Immediately by looking at the function, you cannot say how the function looks like. And there are so many complicated functions, so many complicated functions are there. So in mean value theorem, what we do, we actually, it is not always possible for us to draw the functions. Okay, if I ask you that what is the function, which the diagram which I have drawn, which is the corresponding function, then can you say, I even don't know what function I have drawn. But without drawing, how can we analyze, how can you find the relative maximum and relative minimum? That is the point where, that is our point of concern. And therefore, since always visual inspection and geometry is not possible, so we go for analysis, and analytically we try to treat the particular problem, and we try to find, with the help of analysis, where lies the point of relative minimum and where lies the point of relative maximum. Okay, and therefore we study the mean value theorem. Okay, to get to know where the tangent becomes parallel to x-axis. Okay, and here in this particular case, you see that these things are not happening. Since c1, you diagrammatically also, you cannot, this tangents, if you consider the tangent is not parallel to x-axis. Here the tangent is not parallel to x-axis. Okay, we had the tangents as a part of the straight line like this. Okay, so they are not parallel to x-axis. Why it is not parallel to x-axis? And from there also I can justify that Cn is not a point of relative maximum or relative minimum. C1 is also not a point of relative maximum or relative minimum. So that is why we study. So after that I must say, let us go to the, so this is all about the first paragraph of 6.2. Now I'm going to, after understanding that, I'm going to write the theorem which is given in 6.2.1, which is called interior extremum theorem. Interior extremum theorem. Interior extremum theorem. So it says that let C be an interior point. Let C be an interior point of the interval I, at which I'm enabling the chat box. You can put your attendance over there. So C, let C be an interior point of the interval I, at which f colon I to R, has a relative relative extremum uh, if the derivative if the derivative of f at c exists, if the derivative of f at c exists, then f dash c is equal to 0. Then f dash c equal to 0. So therefore interior extremum theorem says that let C be an interior point. Now there is the question what interior point is. So okay, I'm not going to write any further definition because you will just feel you will not be comfortable. So I'm trying to say it in my own words. I beg pardon to all those mathematicians who have brilliantly defined it, because I may be wrong. uh, in I may miss some line, some words, important words. So with this permission, I'm just to make you understand, and to, from pedagogical point of view, I'm saying that if you consider this interval, okay, so this point is your A and this point is your B. C will be called the interior point. C is called the interior point if you whatever delta you consider for which you get intervals, whatever delta you consider, any interval like c minus delta and c plus delta, all the points of the interval ab, that is x, will belong to that. So then there will be, we will call that no point will lie outside that interval ab, all the points, it is true for all x. Okay, and c minus delta and c plus delta will always be a subset of AB. If this is the scenario, very uh, non-mathematically I have said, so then we call that as interior point. So in our diagrams, C is an interior point of the interval A1, A2. C1 was an interior point of the interval A1, A5. So you see that if we consider the interior point of the interval I at which has a relative extremum, if the relative extremum exists, if the derivative of f at c exists, then f dash c becomes 0. So derivative of f must exist, otherwise if it exists, then is f dash c equal to 0, otherwise not. So what does it mean? Why they have written that if the derivative of x exists, this line is very important. If derivative of f at c exists. So why they have said this? Say for example, if you are careful enough, you see that 0, this point is a interior point. 0 is the interior point of -1 and 1. Okay, but you see, this problem you have done several times. The derivative of the function at the point 0 is not existing over here. So it is not always the case that the derivative will always exist at the interior points. Okay, here in fx equal to mod x, derivative doesn't exist at x equal to 0. So it is also a very important example where we say that fx is continuous in -1 and 1, but not differentiable. So every continuous function, every differentiable function is continuous, but every continuous function may not be differentiable. So that is a very important actually function. So here also you see the c is 0 is the interior point, but at this point the derivative is not existing, and therefore it is not always the case that in the interior points derivative will exist. And therefore they have said that if the derivative exists, then say for here derivatives were existing, and if relative, it's the point of c is the point of relative maximum and c1 is the point of relative minimum, sorry, opposite, c was the point of relative minimum and that was relative maximum, both the cases tangent will be parallel to x-axis. Tangent will be parallel to x-axis. Now I want to ask students that since I have taken, I'm actually taking time to make you understand. So what do you think? Shall I? Was the pace all right for you in today's class? I mean, in your syllabus, Rawls theorem is there, Lagrange's mean value theorem was there like this. So I could have written those. I mean, form theorem statements, okay, and I could have shown you the problems, how to apply Rawls theorem and mean value theorem, Cauchy's theorem, etc., etc. But I have not done anything. I have not introduced Rawls theorem, mean value theorem, anything at all. So is it okay for you, or shall I mechanically teach you what mean value theorem is? So what do you think? Is my approach all right to you, or I shall I move faster? Mechanical treatment I can also give. Whatever you say, I will do. I shall not become angry with you. Don't. I'm just seriously. I'm asking. So if you think that is the option, you are comfortable with this, whatever I've taught you today, then we can go in this particular way. What do you think? Anybody? Don't be afraid of me. I shall not become angry. You know already that I'm not that kind of teacher. Are you comfortable with it? Okay. Okay, okay. So fine, okay, fine. If it is, I think you are representing. Why not? Okay, if it is the, I mean, now there is no point in joining, because this is my last session of today's class. Tomorrow I am going to continue, and many students joined later. I can see. I actually, after seeing that, I actually locked the meeting. Tell those students to be on time. Today I'm not going to take any third session. Tomorrow in morning at 9, again I'm going to continue with this. And so therefore this is your interior extremum theorem. Okay, interior extremum theorem, and you can see the proof of interior extremum theorem in the book. It is in the note. In the interior extremum theorem proof is given. I'm not going to discuss that. The proof is given. Try to read the proof, and I think you'll understand it. Tomorrow I shall go into the discussion. I shall move on to the discussion of Rawls theorem and mean value theorem, and we'll try to solve problems according to that. Okay. So since I have to, no, I do not have any idea when our first first sem examination will happen. I do not have any idea. Okay. So tomorrow we are going to meet at the same time, that is 9 a.m. You can call me later on, Sanjeev, real life perspective. You can call me after 12 today, then we can discuss any real life perspective of this theorem. I'll tell then. Okay. So anyways, bye for now. Tomorrow we are going to continue with topics of Rawls and mean value theorem. Okay. Now real life Sanjeev Pratap, call me after 12:30. I'll discuss with you. Okay. So bye for now. See you tomorrow.